YAG. We all agree that's YAG. What sites are present in the YAG crystal structure, in the garnet crystal structure? You've got tetrahedral, you've got octahedral, and dodecahedral. What's dodecahedral mean again? 12 coordinates. So you've got 4 coordinates, 6 coordinates, and 12 coordinates in this crystal structure, right? Now, how many of these are there? Well, in that formula unit, right, which ones are, like this is the formula unit. Which ones of these are octahedral, tetrahedral, whatever, right? There are clearly 3 plus 5, 8 total cation sites. So those are the ones that are either tetrahedral, octahedral, dodecahedral. How much of each type are there?
There's like 24 tetrahedral, 16 octahedral.
Yeah, I think you're thinking per unit cell. Because right now in the formula there's only 5, or sorry, 8 total, right? So of those 8, how do they get split over these 3 things that I'm asking? 3/5 are tetrahedral. So 3 sites. 3 sites are tetrahedral, 2 are octahedral, and 3 are dodecahedral. Can we go over why? Let's go back to magnetic properties. Right here, right? So you've got yttrium in this example, yttrium iron garnet. Yttrium sits on the dodecahedral sites, all of them. So there's 3 of those, right? 2/5 of the ions are on octahedral sites, and 3 of the 5 irons are on tetrahedral sites. So you must have 3 tetrahedral, 2 octahedral, 3 dodecahedral. And that adds up to 8. Does that make sense? So for this crystal structure, all you have to know is per formula unit, there's 3 dodecahedral, 2 octahedral, 3 tetrahedral. Why is this not working? But it clearly works because I can click it and pull open OneNote. So what's happening?
Is that metal tip or what's it?
No, it's a whole piece of rubber. Why is it not working? Can I draw with my finger? Draw with touch? No. It's the pen. It does, but it's connected because I can do that and pull this up. Why can't I, something's up. All right, anyway. So there are 3 different sites, and there's 8 cations, right? We decided 3 of those go dodecahedral, 2 go octahedral, 3 go tetrahedral, right? So now that we know that, right, I would tell you where things sit probably. I say there's this ion, and it prefers to sit on this site. There's this ion, it prefers to sit on that site, right? So what's the next step? Now that we know where they're at, what do we do next? Find out how many d electrons. Okay, how do we do that? Look at the periodic table.
Also, will one of those be provided, or do we bring our own?
You should probably bring your own this time. And I'll bring a couple extras if needed, or I could always project it, but I think you'll use it on this exam, the periodic table. By the way, you can do one more note sheet from last test. So you had one note sheet from last test. Go bring another one with new notes. It's fine. Okay, what charges do things have to have in the garnet crystal structure? Why is this not work? Yeah, we've got 12 oxygens. That's going to be minus 12, minus 24 total. So these 8 have to add up to positive 24. You can do that a number of ways, but one way which you can do it is have them all be plus 3, right? What else could you do? Have something plus 4, something plus 2, right? So those garnets also exist. This one, what are common oxidation states for aluminum? Plus 3. Plus 3. It's never anything else. What about the rare earths? They're always plus 3 as well. Right? That's a little bit trickier to guess because if you look at the formula or like the periodic table, all these rare earths, plus 3 is like the most common oxidation state for all of them. But it's a bit odd because you think, all right, this series, they lose the 5s, 5s1, 5s2. Why do they choose to lose one more? I don't know the answer to that actually about that. But they are very commonly plus 3. And yttrium is among them. Sorry, yttrium's okay. So yttrium would make sense, right? It's going to lose 1, 2, 3. That makes sense. Why samarium is commonly 3+? I don't have a good answer for you there. Okay, so that said, what's next?
Draw your up and down.
Yeah, man, really wish this worked. All right, let's draw it by hand. Let's do this. This will be fantastic. Okay, so yttrium, well, first off, let's count how many electrons we have. Yttrium, this will be the cheesiest thing ever. No, I can't do it. No. It's real bad, and then it doesn't record, so I will just type it. I'll just type. That's the worst thing ever. There we go. Okay, I'll
Does
just
that
type.
pen not pick it up when you draw it by hand?
No? Something's up. I will figure it out by class, because I'm not going to sleep tonight. It's going to bug me. Okay, how many electrons are left over? Yttrium 3+, we said yttrium has no electrons left. What about aluminum? It's also got no electrons left. We know that by looking at the periodic table, and aluminum, when it loses 3, it's got nothing left. So are there any leftover electrons in this crystal structure? Nothing. Do you expect any magnetic moment out of garnet? Could you pick it up with a magnet? No way. Garnet has no, it's got no, like, dopants, right? What if we changed that? What if we did yttrium, I don't know, manganese garnet? I don't even know if this exists, right? But if it existed, Y3Mn5O12, what might be the magnetic properties of this material, right? Well, yttrium still has no electrons, right? What about manganese? If it's manganese 3+, how many electrons does it have left over? Right there. It's probably got 4 electrons left over, right? If it has 4d electrons, what would that look like for tetrahedral sites? So Mn 3+ on a tetrahedral site looks like what? Where are they going to go? What's a tetrahedral site look like? That's 2 below, 3 above. If it's got 4, there's a good chance it goes low spin. So let's say I tell you that. Let's say that it goes low spin. If it's low spin, meaning they pair up, what's the magnetic moment on the tetrahedral sites? Nada. Right? It's 0. Okay? So Mn3+ on octahedral site looks like what? If it's low spin, no electrons, unpaired. Right? What about this one? Yeah, it's gonna if tetrahedral is low spin, then you betcha octahedral is low spin because it's an even bigger gap. So it's not going to be high spin. But you've got 4 electrons to sit on how many potential orbitals? 3. So you're going to put 1, 2, 3 and pair up one of them. Therefore, you've got 2 left over that are unpaired. Yeah, Barrett?
Unless otherwise stated by you, should we assume that it's going to be low spin?
I will state what to assume, yeah. And never assume something crazy like this. Gosh. Never assume something crazy like this. If it's tetrahedral and you've got 2 electrons, it'll never be that. There's no reason. You guys giggle, but this happens like every test. People write this, right? That'll never happen, right? Because there's no reason for it to do that unless it's a temporary excited state because you pulsed with a laser and it hopped up to that just for a moment and then it's going to collapse back down, right? Similarly, there's no reason why it would ever do that, right? It would never do that because this thing would always want to go there. There's no reason that it has any improvement by pairing up, right? Where it could change is whether it does this with 1 high spin or if that goes away and it puts it there. Because then you're talking about the difference between pairing energy and hopping up in energy, right? Those sort of exchanges make sense, and I have to tell you what to do there. But the other ones are just nonsense. Like, I will take points off of those other ones because they don't make any sense. Okay? So manganese on the, how many octahedral sites? We said there's 2 octahedral sites, and there are 3 tetrahedral sites, right? So there are 2 unpaired electrons per octahedral site, and there are 2 octahedral sites per formula unit. Therefore, we have 4 unpaired electrons per formula unit. That makes sense? So 4 unpaired electrons.
When you say 2 octahedral sites, literally mean octahedral.
Like that's one site,
Okay.
and there'd be another one just like that. And each one of those, we decided, this is tetrahedral, but we decided that there are 2 unpaired electrons per site, right? And there are 2 octahedral per formula. So therefore, per formula, there are 4 unpaired electrons. Are those pointing the same way or different ways?
It's different on people or the same.
They're on the octahedral site, both of them, so they're pointing the same way. If for whatever reason we came up with a scenario where you've got 2 pointing up on octahedral total, but 1 pointing down on tetrahedral, then remember they're opposite directions, so you subtract them from one another. You'd have 2 minus 1 left over with 1 magnet moment. In this case, we have 4 unpaired electrons per formula unit. So we expect 4 magnetons of charge, or of magnetic moment. Sorry, not charge. 4 Bohr magnetons. Okay? Or just 4, that's fine. Any questions on this? What if we took the same thing, but we did, okay, how about this formula? Work this one out with each other. Let's do yttrium 3, manganese 4, chromium, O12. How about this one? Yep. So basically the same as before, but instead of 5 manganese, 4 manganese and 1 chromium. Predict where they want to go. Do your best judgment on this one.
Was it Y3 and then 4 chromium 1?
O12, that's right. I am going to figure out what's happening with this.
Why is always on the dodecahedral?
Yeah, the rare earth, why would it choose to be on the dodecahedral site? Any idea? What determines whether an ion sits on any given site? What things matter? Size is the biggest one. So tell me, how big is a dodecahedral site? It's surrounded by 12 other things, so it's got to be pretty big. How big is yttrium? Bigger than the other ones, right? So it's going to go in the bigger site. So in the garnet structure, your biggest atom will fit on that site.
And do we just always assume that the dodecahedral doesn't contribute to that element at all?
Yeah, because I haven't told you the rule on how the moments are aligned relative to anything else. So I'll never give you one that has any leftover electrons. I want you to take a best guess. I would probably tell you on the exam, but you guys could guess this one. What do you mean, is it similar to spinel?
So in spinel, the lower valence is the tetrahedral side?
No, instead of thinking it that way, think about electron rules on how they like to situate themselves. What makes electrons happy is filled bands, half-filled bands, empty bands. Not pairing up. Those things all make electrons happy. So what would chromium do? Chromium 3+. Yeah. Bugged by this. So the back works and the front doesn't. That's so weird. Right? I can move the eraser around. Tip.
3 on the bottom.
Did I damage it? Like, I wonder if I damaged it.
My question is, does it have like a conductive film on it that it uses?
No, because it's got a bunch of different tips, and some of them are all plastic. Some have a little thing like that. There's a bunch of different ones. What did I do?
When you
with this?
like touch it, does it press the tip in and like activate something?
I'm just
No.
assuming that it's
No, it's really like a light touch. I think it's
I
that.
mean, if you said that it was high speed,
That's great. I wish that I had one of these, then I would probably have fixed it.
No. I'll figure it out.
Octahedral has 3 on the bottom, right?
If the tip works but the back doesn't,
right there, so it loses its.
so I just changed the battery out like a couple weeks ago. I'll try that though.
And it's green. Yeah.
Really?
Flip it around.
That seems dubious, but I will try it.
Sounds weird.
That's what it says on the website.
On the Microsoft website?
Yeah.
All right, I'm in.
But octahedral has 3 on the bottom, right?
Yeah, octahedral's 3 on the bottom.
Now the eraser doesn't work. Yeah. Yes, I don't think it's that. I don't know if the polarity is the issue. Okay, what do you guys think? What's the where's chromium going to want to sit, and how do you know?
It's probably gonna be octahedral.
It's going to be real happy on that octahedral site. How come?
It's got 3 electrons.
It's got 3 electrons and there's 3 sites, so it's going to go 1 on each. Hey,
It works.
Thomas, that makes me so happy.
Who's here?
I am so happy. Check this out. We're doing the rest of this problem written. This is amazing. Manganese 3 plus. Oh, 4 electrons. Never felt so good to write. It could go like that, or it could go high spin. We don't know. Let's assume it goes low spin for a minute, right? So, no spin, right? Meanwhile, chromium, we decided for sure it's going to occupy an octahedral site, and it's going to do that, right? So overall, what would our magnetic moment be in this material? Is it magnetic?
Yes.
It is magnetic, and what would be the magnetic moment? Somebody said 6, somebody said 3. So I think I heard a 5 in there.
Because there's one manganese on and off.
Yeah, I forgot about that. No, you're right. We decided, right, that there's 2 of these sites. I'm sorry, that's tetrahedral.
Are we doing all octahedral?
Because there's 3 tetrahedral sites, and we decided they all give you nothing. They suck, right? But octahedral, you've got 1, 2, 3, 4, and that gives us 2. So 5, the answer is 5. Whoever said that.
Yeah, what?
So there's still 4.
Because think how many there are, right? We had 4 manganese ions and 1 chromium, and we had 5 sites to fill.
Oh, I see.
So manganese will do 1, 2, 3, nothing. But there's a 4th manganese we have to put somewhere. It's got to go on the octahedral site. And we only had 1 chromium. We couldn't fill both sites if we wanted to. We only had 1 chromium in the formula. That makes sense? So whoever said that, I think it was Chris. Good catch. I actually spaced that too. So it'd be 5. These are pointing in the same direction because they're both on the same site. We get 5 there. Yeah.
Is that always going to be the layout of the tetrahedral and octahedral sites? So it's like a 3 and 2?
No, I can give you a fraction, right? What if we did the same exact question, but now we say, let's change it still. Let's do one more variation, then we'll see if there's questions, and if there aren't, we'll move on. Okay, so now let's say we've got yttrium 3, manganese 3.5, chromium, and then what other ion? You guys pick. A transition metal. Vanadium? Do you have vanadium? Vanadium 0.5, right? What will happen now? These are all going to be 3 plus, let's assume, right? Vanadium 3 plus has how many electrons? 2. Where are they going to want to go if you got 2 electrons? Almost for sure tetrahedral, right? So let's draw this out. And if it gets confusing, just draw them all out, right? You know that you've got 3 tetrahedral sites. 1, 2. So there's 1, 2. By the way, who's senior next year? Most of you guys? Okay. You guys will see senior projects sign-ups go around very soon. Well, Jeff and I we just talked to a random project. So if let me just give a quick commercial for one of the projects. It's for the poopery, right? You guys seen this?
Yeah.
This guy wants to make an add-on to toilets that will automatically dispense poopery because it's a gimmicky product, but no one actually uses it because I don't know why. So he wants something that automatically does it, and he wants us to build a device that does so. So if you're super pumped about that, we're actually going to buy a toilet and install it up in the lab and build this thing inside of the top chamber. It's going to be kind of an interesting project. So if that sounds rad, I know, come talk to me. All right, so what's happening? Where are these going to go? We just said vanadium's going to what site? Probably tetrahedral. Is there 1 vanadium per unit cell? No, there's only or per formula unit. No, there's only half. So, half of this thing, right, will look like that. That's our vanadium, right? That's only half of a unit cell. So it means we have another half of a site. Sorry, not unit cell. Half of a site. The other ones, this 1, 2, 2.5, are going to be what? Vanadium or chromium?
Sorry.
We already decided chromium likes this. So that's our 1 chromium 3 plus, right? So that means we've got let me circle them. We've got 1, 2, 3.5 sites that are going to be manganese, right? And those have 4 electrons on them, right? So one goes like that, another one goes like that, this one goes like that, and then this one we decided goes like that. Now it's the magnetic moment per formula unit. And then recall that these things point up and these things actually point down. They're opposite to each other. Okay, what do you guys think? Punch in some numbers. Vanadium's giving grief.
Yeah, like.
Okay, let's just type it out. What would our total moment? Total moment would be what? Let's call negative moment tetrahedral, and positive octahedral, right? Fair enough? So how much negative do we have? We've got, this would be 2, but that's only on a half a site. So it's really 1, right? So we have equals 2 times negative 2 times 1/2, right? Because it's only a half a site that has that. And that's, we decided, is coming from the vanadium, right? Then we've got, anything else?
No.
Nothing else. All 3 other sites have no moment, right? So we can ignore that. So what about the octahedral sites? What are they going to contribute? We're going to have 3, plus 2, right? Fair enough? And that's from, again, this is from the chromium. This is from the manganese. So overall, what do we have? 6? No, because they're opposite aligned, right?
Yeah.
So we got a -1, but we got a +5. It's going to give us a +4. So this has 4 Bohr magnetons.
This convention we set up with 1 up, 1 down, is that the convention that everybody uses, or is that just what you're using?
Well, literally spins have to be spin up or down.
Mm-hmm.
So that is a general convention for it. When you add them up, it's just really positive and negative
Yeah,
values.
so then the tetrahedral are pointing back on the octahedral.
Oh, is that always the case?
Yeah,
So these
yeah,
could be down? No, it's just one, they're opposite each other.
Okay.
Which one's which doesn't matter.
Okay.
Yeah, fair?
My question is, how do we know that 3 of them are going to be tetrahedral and 2 of them are going to be octahedral?
That's,
So we had left
the
over.
crystal structure will tell you that. In the spinel crystal structure, there are twice as many octahedral as there are tetrahedral. There's 2 octahedral, 1 tetrahedral. This one, there are 3 tetrahedral, 2 octahedral. So it just depends on the crystal structure. And the only 2 that we've learned about that I will ask questions on are either spinel or ion.
Okay, so we just need to know that.
So just know these. Know this one, we did the spinels in class. Okay?
So the way we pick these is basically just like level of comfort of each atom, right?
Like, in terms
Like,
of, like,
in
this
terms
guy
of,
likes
like,
to have 2 there.
Exactly, and then we did, of course, we
Yeah.
did vanadium first,
I mean,
then we did chromium.
Again, this is how you technically should do it, but to make grading easier,
Oh, I see.
I don't want like Mitch to be like, well, I don't know where this goes, so I'm going to assume it goes here, and I don't want to grade him wrong for assuming that, but then I have to like grade it
I see, I
a
know.
bunch
So
of
you
ways.
would tell us.
So I'll tell you where the site goes. I'll
Okay.
say, hey, this ion prefers this site.
Yeah.
Fair enough.
Yeah.
Yeah, and if it's ambiguous on the highest and lowest, then I'll also point that out.
So I'm still a little confused on the vanadium. So you
Yeah.
have 2.5 vanadium, right?
There's one. I'm sorry, that's a 0.5. That's just
Oh,
that's an
okay,
ugly
I was,
0.5.
like, so confused.
No, that's me being sloppy. 0.5. Sorry. Any questions on this? Can I answer anything else? We've done more harm than good here.
No.
This make a little bit of sense?
Great, yeah.
Okay.
Very good.
Yeah.
I do have a question. So how are you accounting for the extra half in the manganese? Like I get that you've got 2 tetrahedral and 1 octahedral site, but it's
The other half is
octahedral.
at the very end.
Right, there's actually only 5 sites. 1, 2, 3, 4, 5. But I drew 6 because these are only half each.
Oh, okay. I got you.
However you guys want to do it, whatever makes sense to you, go ahead and do. I'm visual. I like to draw things out and just be quick about it because that's long.
How many questions can we expect for this test?
I think I did 4, but yeah, 4 or 3. I think I at one point had 4. I might have erased it. Josh is looking over it now, so now's the time to plead with Josh to give you an easy exam. If he suggests, I'll change it to. I've already cut out one time.
Are there any topics that
Point on the list that we should.
Nope, I stuck to the list. In fact, there's things on there that we can throw out probably. If when we get to them, I'll tell you. This you need to know.
Okay.
For spinel garnet, you need to know it. Other questions? How would you do this if I said, this was the magnetic moment formula unit, what if I said in 1 cubic centimeter of this material, assuming full density, how it's a magnetic moment? If it was a single crystal, meaning they're all aligned, right? Polycrystal is tricky because then they're all aligned together. But if it's a single crystal of material, how much per centimeter? How would you do that? So many things. What information would I have to give you first off for you to answer that question? You have to know the lattice parameter, and I already gave you the volume.
We can look up the weight of it.
Yeah, the molecular weights
the
and density. You're gonna need to know density. Which I guess if I give you the crystal structure and the lattice parameter, you could determine density yourself.
And you said how many per unit, per formula unit?
So you need to know how many formula units there are per unit cell, right?
Okay.
Right. So that's in the notes. If you want to go back to chapter this
I
one.
also think we have one.
We did.
Yeah. Right, for this one, for example, in a unit cell, there are 16 octahedral sites, 24 tetrahedral sites, which tells you how many there are per unit cell. Other questions? Any more on this? Like I said, I'm not going to expect you guys to guess for sure where the seeds want to sit. I think you guys should have pretty good intuition for it. To make my life easier, great understand of it. Yeah,
So
fair?
the general rule for that is just make sure you're doing the least amount of pairs per site.
Well, the rule is empty, half filled, or filled. Or, and then if you do have the option, don't pair up. Like if you can't do filled, half filled, whatever, right? Like this one, right? It can't do empty, half filled, or filled, so just minimize pairing at that point. These could pair up, but they don't want to pair up. Okay? Other things, should we move on? Let's keep going. If you got more questions, we can come back to it. Next question that you have in yellow anyways
Yes.
was write defect reactions in Kroger-Vink notation. I think that I scrubbed this from the test. Let me double check. Let me not display the exam.
It's okay, we'll study it.
Yeah.
If you're still recording.
I will cut this out. Thank you for telling me. Because I'm looking at it right now. Kim.
Sorry.
Why'd you tell him?
Wonderful person.
I honestly wouldn't have even thought that.
Yeah, I wouldn't have thought of it.
Kim's too pure of heart. Too good. There are only 3 questions. And there's no defect reactions. It's your lucky day.
Can you tell us which ones are on the test so that we can study for those exactly?
We're doing it now. We're doing that right now. Okay, I will cut that out. I'm going to make a note to myself. Okay, Google. Remind me to edit out the exam from my test about 40 minutes in later tonight. Does it know what later tonight is? Okay, next one is use Ellingham diagrams to predict whether...
That's not yellow.
Oh, that's green.
Yeah, green's good.
Green's okay. Are there questions on Ellingham? Jade doesn't have questions. Do other people have questions on Ellingham diagrams? We good? Okay, Barrett?
Just to be sure, things under the line are going to opposite.
Yeah, and if it's ever any question, you should pull up your... It definitely didn't get that. We should find the Ellingham thing here. Where is it?
It's underneath that.
Lower.
I'm blind.
If it's underneath that.
Oh, it's way lower.
It'll oxidize, yeah, 'cause it's lower.
Lower.
Yeah.
If you look at these, like look at some of these things down here. This one down here at the way bottom, that's calcium picking up oxygen to form calcium oxide. How favorable is that? Massively favorable. Down here, magnesium picking up magnesium oxide, same thing. Lithium forming lithium oxide. These things happen, they're way low energy. And the way to think of it is like, this is a free energy scale. It's becoming supremely negative down here, right? And this reaction, this corresponds to the reaction as written. And these are all metal plus oxide forming metal oxides, right? So these things want to happen, meaning it's tough to make them not happen. So you're always going to be above those lines, right? Can you get to a point where lithium oxide will go back to lithium metal? Sure. It's just going to be happening, right? And then things up here in your metals like platinum. Does platinum want to form platinum oxide? Not particularly, right? You got to really work to make it form that, right? So So above it won't happen, below it definitely happens.
And I realized really
Yeah, this is the Gibbs free energy values for different reactions.
This was on the final.
Yeah, if we're having going time.
Can we do a bunch of Ellingham diagrams?
Yeah.
Yes, quite a bit of it.
Of course, that's wonderful. All right, Chris?
So if we had a Ellingham diagram question, what information would you?
Do lots of different ways.
Like the
Forward,
one where
backwards,
you
and do
calculated the partial pressure and then like change.
all sorts of different ways. Right? Because you've got three different axes here that we could use. One is partial pressure of oxygen. So I could say, hey, you pump down the chamber and then you backfill with oxygen to this level. That's easy. That's the easiest case scenario. Then you find the oxygen one, which is this one here. You point it to the O at the top. Draw a line. So bring a ruler if you want, or straight in, right? Then I might be asking for a temperature at which oxidation will stop occurring. Right? I can say this thing is prone to oxidation in this condition, but if you heat it up, at what temperature will it stop? And you say, okay, if it's like, say this material, whatever that is, right? And it's this red line, right? That's your oxygen, that's how much oxygen's in it. What temperature will it stop oxidizing? Or what temperature range will it oxidize? Yeah, if you're above it in this range, sorry, if you're so you're along this line and you go to these temperatures, so you're gonna follow this line. If you're above it, this reaction's happening, right? This is kind of counterintuitive because we think oxidation, that happens at high temperatures. In fact, it doesn't. For almost everything, you go to high temperature and you go below the line and it actually goes back. That's a little bit confusing, right? That's a little bit counterintuitive. So when we say elevated temperature, like this is still pretty hot, right? This is 1200 CK, that is, right? So that's still pretty hot. You got to go to crazy high temperatures for it to not be oxidizing. For actually, it's called dissociation. When you take an oxide and it dissociates into oxygen and metal. Yeah.
The one thing I will ask is, we actually didn't do a ton of this in Connor's class. If you have any examples, like more than the 100, that you could maybe provide, that'd be great. Like, with
yeah, there's a wonderful website out of Cambridge. Let me pull it up. It's really, really good. It's got a ton of examples. Yeah, that's Cambridge.ac.uk. This is really good. They have a bunch of examples.
Okay.
I would check this out. I think it's probably posted in the notes. I will, because Gail wants me to post this anyways. It's right here. Yeah, I will repost this if it's not posted yet. I'll make sure it's up and you can check it out for more examples. Cool? Yeah. Other questions on this, or do we move on? I skipped antiferromagnetism, the origin of antiferromagnetism as it relates to superexchange. Are there any questions on that? Galen and Chris, go ahead, either one.
I was just wondering if super.
It's Galen, right?
Yeah.
I'm suddenly doubting myself. All right.
I was wondering if super exchange was just like a polarization of like an intermediate.
A polarization of an intermediate. No, it has to do with bonding, right? Where's midterm 2? So super exchange, it has to do with having a transition metal, oxygen, transition metal, right? When they're linearly connected by that, what do we know about the transition metals? That you probably have d orbitals, right? So d orbitals might be facing, we know they're going to run along the principal axes of like x, y, z, that we have orbitals running that way. Meanwhile, if this is an oxygen, so transition metal, oxygen, transition metal, oxygens have just p orbitals, right? So if these things are sharing electrons, as they are in most of the cases, that's how they bond. And if you put a spin up here, and this is now they hybridize to make a new bond, an orbital here, then you can put one here, it's going up, this has to be pointing down, right? So if this is up, then this must be down, right? Because this is now one new orbital. We hybridized our orbitals, right? We made a new one there. And you can't put two of the same spin in the same orbital. That's not allowed, right? So therefore, if this goes up, that goes down. Meanwhile, this one has to have one down, one up. So this guy now looks like that's got to be up. And if that's up, because this is another hybridized orbital here, this thing must run out of colors, must go down. Therefore, on the two transition metal sites, this is getting real colorful, this thing's pointing up, and if it's connected linearly by an oxygen between them, this thing has to be pointing down. That makes sense? And therefore they cancel out. This is antiferromagnetism, if you have the same type of ions.
So two atoms interacting with one another, despite having an oxygen in between, a non-magnetic atom in between the two.
Well, let me ask you this: would this work without oxygen?
No, it wouldn't,
Well,
because isn't the oxygen like forcing the,
you could make it work with a transition metal too, because transition metals have these same directions. So you could make another orbital like that, and you're still in that orbital. You can still only put one up, one down, but it could also go in one of the other. It could be hybridized differently. So the easiest, simplest one is when there's an oxygen separating two transition metals. That because of one orbital can't have more than one spin up, one spin down, it leads to this. And so then you got two different sites, whether they're octahedral, both, or tetrahedral, or whatever. You got two different sites, and they're anti-aligned.
Chapter 11.
Yeah.
it is, there's,
Yeah. I had a question on.
Was it? I think it's below. This thing?
Yeah, I guess what do the red arrows between the orbitals mean? Is that just saying that those aren't pairing up?
I don't know. I didn't make this diagram, but I assume that's saying like, hey, this is a new hybridized orbital. These things are together.
there are better pictures online. I found.
For
a lot
super
of-
exchange?
Yeah, I found a lot of good pictures of like each antiferromagnetism, ferromagnetism.
If you guys ever find content, just send it to me. That'd be great. I love to change up my notes. I try and swap them out each year. So if you find good stuff that helped you, send it along. That's good. Other questions on this? More than what I've said, I won't expect you guys to know. If you put an oxygen, which has a p orbital pointing at both transition metals, because you have to share, and because you can't have more than one spin down, spin up, spin down, that leads to antiferromagnetism. Super exchange. Okay. Other questions? Keep going. Okay, so the next one on the list, we're skipping calculate heat capacity, thermal conductivity, thermal stresses. I don't think that's a good idea. Are there questions on that?
I knew how to do this.
Well, let's say this. Make sure you know how to calculate heat capacity, thermal conductivity, thermal stresses. Any questions on that?
Are you talking about like when we did the integral?
Yeah, I'm not going to make you do the integral, but I think it's important to know where it's coming from. Like how to calculate CP, heat capacity, thermal conductivity, and thermal stresses.
Are you
Broadly
asking
speaking.
about thermal shock?
I'm not. Nope, that one didn't make the cut. So, any questions on this, on how you do these and what it's about? Yeah, Chris?
Yeah, so when I was looking at the thermal conductivity, it was like Q equals negative K dx.
Okay, you're thinking of fixed first law definition, right?
Yeah.
Which says Q, the heat transmitted through something by Fourier, they call this Fourier's law, equals negative kappa, right? Thermal conductivity dt over dx, right? That's Fourier's first law. And kappa would be the thermal conductivity there. That's one way to do it, yeah. In class, she said the integral thing. What's she talking about? In class, we talked about heat.
Stress.
What's that?
Wasn't it thermal stress that we did?
Oh, you're talking about a different integral thing. I'm talking about this one. So thermal conductivity, the rate at which it moves, you have to take into account the integral. Can you just do this? Will this work? What? I can use some of this, actually.
Yeah.
Oh, jeez. I don't know. This is not worth my time. Okay. What goes to calculate thermal conductivity? You need heat capacity. You need phonon velocity. Let's just call that lambda. And then you've got, what else? You've got your scattering distance, right? Remember the example we did was like,
Phonon velocity and then that's it.
oh, I think we use capital gamma for scattering sites. And then we've got phonon velocity. We'll call that V. I messed up my variables. And we did this over all frequencies, right? So starting from your zero frequency, like of your wavelength of phonons, all the way up to whatever, right? Your maximum frequency over all frequencies. So this is EW out here.
So in the notes that you have it as the wavelength, but
Frequency, wavelength, same thing. Yeah. Well, we could use either, right? Make it smirky. Right? So from your smallest wavelength to your highest wavelength, to your smallest frequency to your highest frequency, you have to sum it up over all your different phonons that can contribute to heat, how much heat can it carry, what's the speed of that phonon, and how often until it's scattered, right? So the bucket brigade means the size of the bucket going down the line, that's like heat capacity. How much heat can each one carry? So this is, right? Then you've got this rate at which it goes down the line, that's the phonon velocity. And then this gamma term, that's how often it scatters, how often you drop the bucket, right? All this goes into calculating thermal conductivity.
It's called how often it's scattered.
It's called the mean free path.
Well,
Yeah, its name is the mean free path, but what it represents is how often there's a scattering rate, the distance between scattering events. So it has the units of length. Yeah, Barrett?
That would be a value that you would give us, or one that we have to
I'm not going to make you use this. I'm just reminding you guys where this comes from, right? So basically, you get kappa from here, from Fick's first law, Fourier's law, or you can calculate it from this. Okay, what about heat capacity? What should heat capacity do? Q equals what now? Oh yeah, okay. Yeah, so for heat capacity, CP, the heat capacity should tell you how much heat goes into something to change some amount of something, call it M, some amount of temperature change, right? Like so. They'll report it as joules per gram Kelvin, and then it's like to raise a gram of substance, a degree temperature, right? It tells you how much energy, or it could be per mole, right? They do both of these. What should it reach at high temperatures? Does heat capacity, what's it do as a function of temperature? It asymptotes out, right? So as temperature increases, your heat capacity value should have a T cubed value, and then it should asymptote to 3R. 3 times the gas constant is the Debye limit, right? They call this the Dulong-Petit limit or the Debye limit for heat capacity. Okay? When does it reach that? When you are at the Debye temperature. When that value is 1. When your temperature divided by the Debye temperature for your material is 1, you should be pretty much asymptote, right? And the Debye temperature changes for all different materials, right? For diamond, it's really, really high, I think. Yeah, diamond's high. Things like lead telluride are super low. We didn't cover on how to guess those in this class. Okay, so that's thermal conductivity capacity. How do you calculate thermal stress?
epsilon equals alpha over delta T and alpha being
So
thermal expansion.
epsilon, the strain that's produced by something expanding, is equal to alpha, it's thermal expansion coefficient, or the coefficient of thermal expansion, divided by, what was this, delta T, did you say?
T,
Yeah.
which is also equal to sigma over.
Is that right? Alpha over delta T, or is it times? Is that right? You might be right, Jay. I'm just gonna double check. I don't remember. You're probably right, but I'm just gonna double check.
Alpha is just over temperature because your delta L over L naught.
So this is strain. So it's actually multiplied. It's actually multiplied, right? Another way we could write the same thing, since that's strain, that must equal alpha times delta T, not divided by. That makes sense? So it's multiplied by. Okay, so that's how much strain arises. So if you've got two materials and you peg them together, right, and you heat them up, what's going to happen? What sort of stresses will arise? Barrett?
Shear stress. They have different-
Technically, yeah, it'll be a shear stress, but I mean, it's interesting. Yeah, it is a type of shear stress, but still, what's the magnitude of it? What's the expression for calculating how much? Two materials, A and B, right? So you've got A and B. You've got the coefficient of thermal expansion of A, and you've got the coefficient of thermal expansion of B. What else do you need to know? Anything?
Volume.
The what?
Volume of A.
Nope. Don't need to know the volume.
The contact surface area.
Nope. Don't need that. So let's just say we got you've got this thing, that's A. You got this thing right here, that's B. At room temperature, they're the same length, and you stick them together, right? You bond them together in some way, okay? You heat them up, right? So you've got a delta T. What else do you need to know the stress? Yeah, you need to know the Young's modulus for each material, right? So you've got like an E for A, and you've got an E for B. So if I asked what's the stress that's generated in material A, what would it be? What's the stress that's generated in material A?
The strain times the modulus.
Strain times modulus. And we've got our strain right here, right? So the stress in A is going to be equal to the modulus times A. It's how it responds to a force, right? This is telling us, is it compliant? Is it stiff, right? Multiplied by, what's the strain going to be? Say again?
It depends on which one's bigger, right?
Well, it's divided by alpha A over delta.
So what did we do on the homework? We had yttria and we had yttria, stabilized zirconia, and we had alumina. What did we do? I can like see Ashley saying it.
Well, yeah,
Took the difference. It's the difference. You take the difference, right? Because they're both going to expand, probably, find some material strength, but most of them expand. So does A expand more or less? We don't know, right? But we have some expansion coefficients, so it's going to be the difference, right? So take alpha minus beta. Alpha A minus alpha B. Sorry, I'm getting sloppy.
You can still always do the larger minus the smaller.
Yeah, how do you do this? Like, let's say that if this is larger, right? So this is like 10 ppm, and this one's 8 ppm. Then which one's going to expand more when you heat this up? If you let them, if they were unbonded, which one expands more? A, for sure, right? So if A wants to expand more, but it's limited, it's constrained by B not letting it, it's under tension or compression.
It's under compression.
It's under compression, and B is under tension, right? So then, I guess whether you A minus B or B minus A, it doesn't matter. You're going to get the same value. We'll just change the sign of it. So as long as you can reason in your mind which one should be under tension or compression, it doesn't matter.
Why does B under?
Because A wants to stretch even more than B. So A's outrunning B. So A's feeling squished, like A's being like, come on, it's being squished, and B's being like pulled along. Right? So it's
So
being under tension.
wouldn't this convention work either way? You would get the right sign because you would have. I mean, if you did
Let's do it. Let's
sigma
plug in
A,
values.
sigma B equals Young's modulus B.
Let's plug in some values, right? So 10 and 8, and delta T will be like 100, right? Right? So when you start plugging this in, remember these are 10 ppm per K. Quick question, do I need to convert 100C then into 373 Kelvin? No, because we're talking about difference. And Kelvin and Celsius are on the same difference scale, right? They're shifted relative to one another. So this is where the delta T, right? If this was absolute temperature, yeah, you would have to do it. Where it's the delta T, it's still 100 degrees, right? 100 degrees C equals 100 Kelvin. We're talking about differences, okay? So go ahead and plug this in, right? If the modulus is, I don't know, 100 gigapascals, 100 GPa, then you've got 10 e to the negative 6 minus 8 e to the negative 6 times 100. What do we got? Somebody got a calculator? Did I bring mine? Yeah. 0.2? I don't know. Let's find out. Zero 0.02. 0.02. So I get a positive 0.02 gigapascals or 20 MPa, right? Yeah, 20 megapascals. So that produced 20 megapascals of stress in material A. If your material B has a different modulus, it's going to produce a different stress, right? Because the strain is linked. Like both of these things have to expand the exact same amount because we mechanically stuck them together up until the time when it breaks, right? When it fractures. So strain is, this ain't changing, right? That's stuck to both materials. But the amount of strain that produces will produce different amounts of stress depending on what your constant proportionality is, your elasticity is. Okay? Any questions? So this turned out to be a positive number. We're talking about material A. We said it's under compression. So by doing A minus B, we got a positive number. Normally we think of negative speed compression. I would think more about just knowing which limit tension compression than relying on the sign together, right? Okay, fair?
So then if we wanted to do this for B, we would do the same thing, just
Change this out for degrees. And then recognize it's going to be tension as opposed to compression. Any questions? Keep going. We're 1 hour in. We're halfway in. Okay, let's keep going. Next one is thermal shock. There's no question on that. Identify changes in ferroelectric/ferroelastic/ferromagnetic behavior as it relates to crystal structure changes, applied fields, and stresses. So let's talk about that. First off, what are these things? What is a ferroelectric material? What field do you use? What result do you get out of it? Ferroelectric. You use an electric field, hook a battery up to two ends of it, and what do you get out of that? Yeah, you get a polarization, right? Meaning that you can accumulate current on this thing, right? So that means that somewhere inside the material you've got domains. What's a domain? It's a region of alignment, right? Where you've got domains now that will polarize in that same direction, right? Okay? What about ferromagnetic? What's the field you apply here? You can apply a magnetic field to it, and now your domains are still the same domains as before. They don't feel like the same literal things, but they're a region of aligned now magnetic moment, right? Meaning they're pointing, some region of unit cells all point in the same direction, right? Ferroelastic, what was that one? Yeah, now your field is a stress. You apply to it, what do you produce? No, that's a piezoelectric, you know. Ferroelastic means you're going to have domains of elastic response, right? Elastic response means like maybe the unit cell squishes, right? So you're going to have some domain, some group of unit cells that all squish in the same direction, right? Or pull apart in the same direction, right? They have an elastic response that depends on the domain. And this is an interesting one, and this is what actually Professor Birker in our department is super famous for, as we will learn in a couple chapters, because it turns into a toughening mechanism in ceramics. Yeah, Barrett?
So is that like when you pull a rubber band, now you're going this way and that's this way?
And let's wait till we read Birker's paper on ferroelasticity before we go into more detail on it. Because it's better when we talk about toughening of ceramics. It fits better in there. Okay, so that's these concepts. How does temperature play a role in these things? What to remember here is the demo we did when I had you all close your eyes and point your arm in a random direction. Close it again. Everyone close your eyes. Point your arm in a random direction. Open your eyes. This is above the Curie temperature. Thermal energy is so much so that arms are just like every which way. Dipoles, domains are all oriented. They're not oriented. They're just completely random, right? You go below a certain temperature called the Curie temperature. There's actually some other names with ferromagnetics, but we're just going to call it Curie for now. The Curie temperature, where it spontaneously orders. Not the entire, all the way through, but some domain. Some number of unit cells spontaneously order in the same direction, right? You go below, for example, in barium titan, it's like 120 degrees Celsius. You go below 120 degrees Celsius, and all these dipoles just shift on their own. Like the titanium, all within some domain, they all go one way, oxygens go another, and you're left with a net polarization in that dipole, right? How do you maximize this? How do you make as many dipoles as possible all point the same way? You would apply an electric field to this thing as you go above the 120 degrees C, below it, right? As you do that, it's called poling. You try and make it look like a single crystal by doing that. Now, it won't ever be as good as a single crystal, but you can get pretty good at it.
So you apply an electric field throughout the entire time that you have, or above the Curie temperature.
Because above the Curie temperature, right? So again,
It's
back to the
random.
example where your arms are like every which way, it's random. If I apply a field, all those arms will still line up to the field, right? It's just that if I take the field away, then they go back to being all whatever they want, right? So if you apply the field above the tree temperature, it's lined up, and then you just basically freeze it in that orientation. And then if you switch the field below the tree temperature, they should all switch more or less together. And there's always going to be some fraction that don't. Okay?
So you can use an electric field for ferroelectric, magnetic field for
Stress here. Yeah, exactly. Okay? What do the hysteresis curves look like? You're going to use some sort of field to change things. So this is either M, or your electric field, or your stress, right? And then you're going to achieve, actually, they call this H for magnetic field. That's your magnetic field. You're going to achieve a magnetization, a polarization, or some strain, right? And then your curves can look different. It can be like this, where there's a significant amount of remnant polarization, remnant magnetization, remnant elasticity, right? Or I guess you just call it strain. Strain, you'd call it, right? Or it can be very, very small. It could be like this. Let me just draw it again. It might look like this. We call this hard and this soft. So a soft ferromagnet is one like this. What does that mean? It means you can polarize it, and it's polarized pretty easily, so you can see here. So you polarize it, you magnetize it, you align the domain pretty easily. But when you take that field away, the magnetic field, you're only left with a very small residual magnetic moment, right? And there's pros and cons to all these things, right? Is this good for a hard magnet that you want to use to stick things to? It's not great for that. What's it good for? Yeah, something that might need to switch very quickly. Memory, for example, there's a trade-off. You want your memory to be able to store. You don't want to lose this. You want remnant magnetization, but you don't want like a huge field to make it switch. So there's some applications there, right? So we talked some about these. But that's hard and soft. All right, what else? Did we cover everything here? Identify ferroelectric, ferroelastic, ferromagnetic behavior as it relates to crystal structure changes, applied field stresses. Could you calculate a polarization for different ferroelectric materials? I don't think we had that question. I think I got it. Okay. Keep going. That's it. That's it.
You say you got rid of shock resistance?
Thermal shock resistance didn't make the cut.
So at the very end of that, I just want to mention something about like question number 8 on this last homework.
Okay.
It was pretty intense, and like I don't know if I fully understood it.
Yeah, we can do that. Actually, you guys already turned that in, so we can actually do that together if you guys want. I haven't worked that one out yet, but I'll show you how I would go about it.
Okay. Are solutions for that one going to be posted?
Yes. So today's Wednesday. I will see if Josh can have those by tonight, and we'll get them posted. I bet we can. If not tonight, then by tomorrow, I think. So this one, okay, pure MgO. I tell you how many shock key defects there are, right? And I say how many electronic defects there are. And it turns out that there's way more shock key defects than there are electronic, right? There's 2 orders of magnitude greater, basically, right? Meanwhile, I give you the mobilities of these two things, and the electrons are about 3 times more mobile, right, than the ions. Oh, sorry, no. I give you electron hole mobilities. Do I give you ionic mobility?
No. That's what I guess this question confused me because I'm not sure if shock defects are the same as hole defects.
What's a shock key defect? That's, think of like a mnemonic device where I think that you shot a hole right through it, and as it went through, it took out 1 cation and 1 anion. You shot a hole right through it. So they're just missing ions, right?
So these are these aren't like doping things. It's like physically.
Nope. It means that there's a vacancy on a magnesium and an oxygen site, right? Okay. So it says, given that the much larger concentration of cation and anion vacancies, one might expect this material to primarily be ionic in conductor, right? Because there's 1.4 e to the 11, and there's only 3.6 to the 9 per electrons. So you think, oh, we got all these extra vacancies. Maybe vacancies are going to dominate the electronic contribution. You'd expect that, but it says, I must have said somewhere here. I must have you calculate it. I forgot this one. Turns out the mobility is actually much lower. Do I have you solved for mobility in this question? I thought I did. Oh, I give you this, so you can solve it using that. So it says ignoring oxygen vacancies, which are slower than the cation vacancies. Use the diffusivity information for magnesium vacancies to calculate the ionic transference number. What do I mean by ignore it because it's slow? What I mean is that your overall conduction will depend on, if it's going to be due to ions, you've got to have magnesium 2+ and oxygen 2-, like I'm writing with a Sharpie. Built-in color thicknesses, right? You have to have both of these traveling. You can't just have one of them, right? You've got to have both. Because if magnesium only is able to travel, then as it travels, it's going to build up a delta positive and a delta negative, which will eventually resist further magnesium from traveling, right? So you have to have both of these. So when I say magnesium travels way faster than oxygen, is that what I said?
Yeah.
Which one was which?
Oxygen.
Then the one that's going to limit your ionic conductivity is this one. You just say, all right, this one will always be as fast as oxygen, so figure out what oxygen is. Magnesium's faster, they're the same, right? So what's the rate at which this thing moves? Once you know that, that'll tell you the ionic conductivity, right? The electrical conductivity coming from ions. Yeah, Barrett? No. Okay. That makes sense? That part at least makes sense?
Ignore that part. The question says ignoring oxygen.
What do we say? Sorry, let's read it again. Make sure we get it right.
Yeah,
So I said, ignoring oxygen vacancies, which are much slower than cation vacancies, that must be much faster. I must have done a typo there. Because you need to figure out the slower species. That's got to be a typo. I will confirm that, but it must be a typo. Does that make sense? Why though? Like whichever one goes faster, it doesn't matter. You're limited by the slowest species if you have coupled transport. You have to have both of them going. You're going to be limited by the slower one. I think I mistyped that. Right? So it says calculate the ionic transference number. What does transference number even mean?
Conductivity that comes from the ions or something like that.
So the transference number for ionic conductivity is the fraction of ionic conductivity over the total conductivity, which might be just from ions and electrons, right? Right, that's the transference number. Fair enough? So I say use the diffusivity information for magnesium vacancies to calculate ionic transference. I give you the activation energy, I give you mobilities for the electrons and holes, and I give you the diffusion pre-exponential for magnesium vacancy motion, right? The D naught means the pre-exponential for diffusion, vacancy on a magnesium site, right?
The first part was fun.
So how do you set this up? What do you need to know? There's like equations.
First solve for G. First solve for G, and then there's a large ionic conductivity.
Right, so we'd find it. Let's go take a look at it. I don't know if I remember it offhand. Ionic transport is going to be right here, right? Here's our ionic transport, going to be F, D, N, Z, E, K, T, right? So F, I think I had Josh tell you guys just to assume 1. So basically, like imagine like a square grid like this, and you've got an electric field that's wanting Jerry to travel that way, right? Or let's say a vacancy, right? This vacancy wants to travel that way, right? So the geometric factor basically says like different crystal structures, for it to make a step in the direction of the magnetic field, or the electric field, can it take a direct step, or is it going to have to be like some off step, right? Right. Plus, like in this case, it's surrounded by 4 chairs in plane, and then like one above, one below. So it's got 6 options where it can go, right? So 1/6 of those would actually move in the right direction. So those geometric factors have to do with that. Like how many of the possible hop directions, how many give you the right direction? So technically, this can be fractions. It can be like 1/6 or whatever. We're going to assume 1 for right now, right? D, this is the diffusion of that species, the diffusion coefficient for that species. In this case, we're talking about vacancies of magnesium, right? So you need to figure out what that is. How do you figure out what that is? You have to remember that diffusion is
EXP and
Yeah, D of some species, let's say for magnesium, is equal to D naught times the exponential of the negative activation energy for diffusion over KT, right? So I gave you the activation energy of this question, and I gave you D naught. So you can solve for what the diffusivity will be at whatever temperature this is at. Then we need N. What was N? That's carrier concentration, right? So in this case, it's the concentration of vacancies or whatever. And we know what those are. We know what our Schottky concentration is, right? Z is what? Yeah, why does that come into conductivity? It's all about charge. It's all about charge transfer. If you've got an ion like titanium 4+, if it's able to move, it's taking the equivalent of 4 electrons at a time, right? So it's going to give you great charge.
They're waiting for class down there to do it.
So we're safe?
We're good.
E then the fundamental charge of them. So how many charges is it carrying, and what's the charge of a charge, right? So 4 times fundamental charge divided by KT, right?
It's 2 for us.
For this one, it's 2 because magnesium is 2+, right? So it'd be 2 times 1.609 to 1019 coulombs. Okay? Any questions on that? So that's your ionic conductivity. How do we determine electronic conductivity?
Sigma E equals NE times mobility.
Yeah, we said that conductivity for electronic is going to be equal to N, right? That's the number of electrons. You don't usually write the sub E. Times the charge of an electron times the mobility of electrons plus P times the charge of those things times the mobility of holes, right? And we know N and P are equal in this case because we're talking about, what did I call them?
Intrinsic.
Yeah, I think I used the word intrinsic for somewhere. Yeah, electron intrinsic. So that means we have the same amount, right? So N equals P, and we've given you the number. You know what the charge is, and I gave you the mobilities. Okay, any questions on that? Straightforward. What's the next one? B says, rather than pure MgO, now consider MgO that we've doped with 400 moles 400 mole part per million aluminum. Am I missing a word there? 400 mole parts per million of aluminum. I think there's something missing there, but I told you what the concentration is, right? So now you've doped it, right? I think I've said something wrong there. 400 mole ppm, oh, aluminum, right, okay. The dopant is aluminum, and it's 400 mole ppm, right? If aluminum sits on a magnesium site, consider how many cation vacancies this will create. So I've told you, in this material, you have this number of aluminum on it, right? Sitting on magnesium sites. There are 2 e to the 19. Huge number, right? Relative to where we were at before. We were at like 1 e to the 11th before in terms of intrinsic carriers, or intrinsic vacancies. Now by putting this on there, we know we're going to have more, but how many more? Is it for every one of these do we get a vacancy? Or a different number? And aluminum's 3+. So an aluminum 3+ on a magnesium site, that can't create 1 vacancy. It's got to be for every 2 aluminums on a site, that creates 1 vacancy. So this number divided by 2, that's our new number of vacancies. Technically, the number is actually the number from before, which was 1 e to the 11, right? So it's 1 e to the 11 plus, what is it, 2 e to the 19 divided by 2, which is 2 e to the 19 divided by 2. The 1 e to the 11th is so much smaller, we just ignore it, right? The intrinsic number of Schottky vacancies, it's so small relative to that, you can just ignore it. Or you can include it, it's going to change the answer. It's so much smaller. Right, Barrett?
You just go really quickly how you got the 2 aluminum equals 1 magnesium.
Yeah. So an aluminum is normally 3+. I'm writing all over this. This is a little bit sloppy. Aluminum is 3+. So if it's on a magnesium 2+ site, then it's overly positive by 1. So you have to have charge neutrality. So the crystal can choose lots of things to fix that. You can put aluminum on interstitial sites, do all this stuff, right? What it's going to do is make oxygen vacancies, right? Right. You're going to take away some negative.
If you took away negative, what would become more positive? It's already positive.
Okay, let's see. Aluminum is 3+. You're putting it on a magnesium site. I made it
So then extra positive.
Oh, I'm sorry. This is not oxygen. It's going to create magnesium. Excuse me.
Magnesium vacancy.
Magnesium vacancies. Which is, we're talking about magnesium diffusion anyways. Alright, I'm just talking about oxygen vacancies. I messed that one up. So let's start over. You put an aluminum 3+ on a 2+ site, it's overly positive, right? To fix that, we need to remove some positive or add some negative. We're not going to add negative because you're not going to stuff an extra oxygen in this thing. You're going to take out some positive. So you can't take out one charge. The smallest you can take out is 2 charges at a time because we only have magnesium 2+, right? So for every 1 aluminum, we have 1 extra charge. If we took out 1 magnesium, now we don't have enough charge. So for every 2 aluminum replacements, we're +2, and we can take out 1 magnesium. Yeah,
So the oxygen is there.
Oxygen is unchanged.
Okay.
Yeah, I said that wrong. I apologize for that.
So basically, we put in 2 aluminum and we take out 3 magnesium.
You substitute 2 aluminums and you take 1 magnesium out.
Okay.
So overall, we've lost 3 magnesium.
You've lost 3 magnesium sites.
sites.
You haven't lost it. I mean, you've lost 1 magnesium. You've replaced 2 of them with aluminums. Okay. So it says if aluminum sits on that, how many blah blah blah. Use this to calculate the ionic contribution to electrical conductivity, right? So now you go back just like before. What's different? We've got a new number. Oh, it was on the other sheet. We're going to do this again, but now n has changed. This was like our before it was just the Schottky number of magnesium vacancies. Now it's the Schottky number plus this other one, and it's going to be so much larger than this thing. It's like 7 order magnitude larger. It's way bigger, right? 10 million times bigger. So then it asks what? It says the next part. Now consider oxidation reaction given there, right? You start out with oxygen on an oxygen gas, and then you've got these vacancies of magnesium with oxygen gas, right? So what used to be an oxygen vacancy, it gets filled with this oxygen gas, but for charge neutrality, the only way that can happen is by creating extra holes. That's what that reaction is essentially saying. That you start out with all these oxygen vacancies, you're going to start plugging them up with gas, oxygen gas, and that's going to change the number of defects that are present. Before n equaled p, but now you're adding extra holes, so p is going to start to become larger, right? So I give you the equilibrium constant for that reaction, this one here. So it's this, it's got some energy associated with it, right? It says calculate the whole concentration caused by this oxidation reaction, right? So this whole thing will be equal to the equilibrium constant for that. So you're just going to take h squared times however many of these there are divided by the partial pressure of oxygen to the 1/2 power, right? I say the temperature, I say that it's in air, so you know the partial pressure of oxygen. So now you can solve for the number of holes. And just like before, I think that the number of holes that you get are so much larger now than the number of electrons intrinsically that you can basically ignore the intrinsic component because it's going to be really small. Or leave it in, fine.
So we're assuming that the oxygen on the oxygen sites is just equal to 1.
That's one, so you ignore it. You ignore the rate constant. And then the last one, calculate the ionic transference number for the aluminum doped magnesia as measured in air. So it's just taking this value and calculate the transference number.
Were we given the pressure
In air, it's about expect everyone to know that it's,
Oh, I
it's
just want you to
21%.
know, I was just thinking we were missing something, because right, we're solving for the holes.
No, that's equal to 1.
Oh, so right, let me just write it out just to be clear. You've got K. K is the equilibrium constant, so you take products over reactants, right? So it's going to be P squared, or H squared if you want, right? P squared, multiplied by 1 oxygen site, that's just a neutral species, we're going to ignore it. It's 1, times the concentration of our magnesium vacancies. I don't know what just happened. That will all be divided by the partial pressure of oxygen to the 1/2 power. And you know these things, so you can solve for P. Okay? Once you know that, it's pretty straightforward to wrap this one up. Again, P, what can carry electricity in this thing? Electrons and holes. and there's those that are intrinsically created, and this is like in addition to those intrinsically created. Right? So what's really interesting is that as you change partial pressure in these materials, you can see the transference number change. It could go from being like a solid ionic conductor to an electronic conductor. And in fact, it does both. It goes ionic up to electronic, and then it goes back to ionic again. And the reason why it does that is because this defect reaction changes. It stops being the dominant defect reaction. Different ones happen at different partial pressure levels. We're not going to get into that in our class. When we take Shetty ceramics class, we'll do more of it. Okay. Other questions? Anything else for the exam?
So, did you say that we are, or we're not doing the calculated defect concentration dependent on partial pressure box? That's kind of,
Don't go to do it.
okay,
That's not on this exam.
Okay.
I might put on the final, but
not the
the final we cover so much, I don't know if I'll put on there either.
Yeah, we just calculated the defects based off of our.
But this is kind of covering that, like, it's the same.
This would be too hard for a test question. I think this would terrify people. But I would. This
I'm
is
just
the type
saying
of
the
question
principles
that
is the
would
same
be
for that
built
type of
around.
thing.
Yeah. No, homework questions should be harder than test questions. I think
Yeah.
if you've taken my class before, homework questions should be a pleasant surprise, or test questions should be slightly easier than the homework ones. Garrett?
You just reminded me really quickly about ferromagnetism.
Yeah, what's the difference between anti-ferromagnetism, ferromagnetism, and ferrimagnetism? A ferromagnet has what? Domains are only in one direction, right? It's not like you've got 5 more magnetons than 4 and a leftover 1. That would be ferrimagnet. Or it's not like a anti-ferromagnet where you've got like +2, -2, overall nothing. A ferromagnet just has in one direction.
Okay, so ferro is all pointing in the same direction. Ferry is some pointing up, some pointing down, and then anti-ferromagnetism is they cancel each other out.
Yeah, it's ferromagnet, they're all pointing the same way. Anti-ferromagnet, they perfectly cancel out. Ferrimagnets are when you add up positive and negatives, but there's something left over. Ferry. Okay, good. Any questions? So bring an extra sheet of notes. Bring a ruler if you want. Bring your periodic table, I suggest. And good luck.